An invisible barrage of atomic shrapnel is piercing your body this very second. These are cosmic rays, the universe's most energetic particles, fired from unimaginable violence across the cosmos. By the end of this journey, you will understand the 50 astonishing truths behind this silent rain, from the cosmic accidents that create it to the profound mysteries it still holds. We will uncover what propels a single particle with the force of a major league fastball, and why the most powerful events in existence leave no visible trace. What hidden story do you think these ancient fragments are trying to tell us? That silent rain has been misnamed from the very beginning. The first fact to understand about cosmic rays is that they are not rays at all. The term is a fossil, a relic from a time of scientific mystery over a century ago. When these invisible signals from space were first detected, their true nature was completely unknown. Physicists of the early 20th century, armed with the knowledge of X-rays and gamma rays, naturally assumed this new phenomenon was another form of penetrating electromagnetic radiation. They called them rays, and the name, however inaccurate, stubbornly stuck. In truth, what rains down upon us is a hail of solid matter. Cosmic rays are almost entirely high-energy particles, the shattered pieces of atoms themselves. The vast majority are single protons, which are the bare, positively charged hearts of hydrogen atoms. The rest are heavier atomic nuclei, like helium or even iron, stripped of their electrons and hurled across the galaxy. These are not beams of light, but microscopic bullets of actual substance, each one traveling so close to the speed of light that it carries the punch of something far larger than its size. It is a fundamental correction that shifts our entire perspective. We are not being illuminated by mysterious rays. We are being sandblasted by the raw, energetic building blocks of the universe. These atomic bullets move at speeds that defy human engineering. The second astonishing fact about cosmic rays is their sheer, incomprehensible velocity. The most powerful particle accelerator we have ever built, the Large Hadron Collider, can hurl protons at a staggering 99.999991% of the speed of light. It is a monumental achievement of human science, yet the universe operates on a different scale entirely. The most energetic cosmic rays we detect have been accelerated to energies millions of times greater. To put that into perspective, if a proton circling the tunnels of the Large Hadron Collider is a Formula One race car screaming around a track, then an ultra-high energy cosmic ray is a starship. It is traveling so close to the absolute speed limit of the cosmos that from its own perspective, a journey across our entire Milky Way galaxy, a distance of 100,000 light-years, would take mere minutes. It is moving at 99.9999999% of light speed. That string of nines is not an exaggeration, it is a measurement. At such velocities, the rules of our everyday reality warp and bend. Time for the particle slows to a crawl relative to us, and its mass effectively balloons, packing the kinetic punch of a professionally thrown baseball into a single subatomic speck. This is not just fast, it is physics pushed to its absolute extreme, a demonstration of cosmic forces so violent they can take a fragment of an atom and make it the fastest moving object for light years in any direction. Where in the universe could such an unimaginable particle gun possibly exist? This relentless bombardment is not a rare event, it is the permanent condition of our planet. The third fundamental fact about cosmic rays is their absolute ubiquity. They are a constant, invisible rain pouring down upon Earth's atmosphere from every direction in the sky. There is no shelter, no moment of the day or night when this silent hail of atomic fragments ceases. It is a natural and inescapable part of our environment. To grasp the scale, consider your own hand. Roughly once every second, a cosmic ray particle, often a proton traveling at nearly the speed of light, will pass straight through the palm of your hand. It happens as you read this, as you sleep, as you go about your day, an unseen subatomic visitor leaving no trace as it traverses your body. This makes cosmic rays a significant component of our natural background radiation. The air we breathe, the ground we walk on, it all contains trace amounts of radioactive elements that contribute to this background, but from above comes this steady drizzle from the depths of space itself. It is a humbling reminder that we do not live in a sterile, isolated bubble. Our world is immersed in a cosmic ocean, and these particles are its most energetic waves, washing over us in a ceaseless, silent tide that has continued for billions of years. This constant rain presents us with a profound and enduring mystery. The fourth, and perhaps most compelling, fact about cosmic rays is that for over a century, we have struggled to discover where the most powerful ones actually begin. Identifying the exact cosmic accelerators, the unimaginable engines in the void that can fire a single proton with the energy of a fastball, has been one of astrophysics' greatest detective stories. The challenge is not a lack of suspects. We have a list of extraordinarily violent candidates, from the crushing magnetic fields around supermassive black holes to the shockwaves of exploding stars. The problem is the evidence itself. Cosmic ray particles are not neutral travelers, they carry an electric charge. This makes them vulnerable from the moment they are launched to the invisible web of magnetic fields that fills the space between stars and galaxies. Think of it like trying to trace the path of a pinball by only listening to the final bumper it hits. Each magnetic field the particle encounters gives it a slight nudge, bending its trajectory in a gentle, unpredictable curve. Over millions of light years, these countless tiny deflections scramble its path completely. By the time one of these atomic bullets finally strikes Earth's atmosphere, it points back to a meaningless patch of sky, its true origin lost in a cosmic maze. The universe has fired a shot at us, but the gunshot echo has traveled through a hall of mirrors, leaving us to stare at the bullet and wonder where the shooter is hiding. This cosmic detective story does have a prime suspect for the lower energy cosmic rays. The fifth fact is that for a large portion of these particles, the likely culprit is the death of a star. When a massive star exhausts its nuclear fuel, its core collapses in a cataclysm known as a supernova. The explosion that follows is one of the most energetic events in the universe, for a brief moment outshining an entire galaxy. But the true cosmic ray factory is not the brilliant flash of light we see. It is the invisible aftermath. The explosion blasts a colossal shockwave of gas and debris outward into space at millions of miles per hour. This shockwave plows into the thin, scattered gas that floats between stars, a region known as the interstellar medium. Picture this shockwave as a titanic, invisible wall moving through a fog. Now imagine a single proton from that fog, a lonely hydrogen nucleus. As the shockwave approaches, the proton gets caught in the chaotic, churning magnetic fields carried along with it. It is swept up and hurled forward, bouncing back and forth across the shock front like a ping-pong ball trapped between two closing walls. With each crossing, the magnetic turbulence gives it another kick, another boost of speed. Over hundreds or thousands of years, this process, called diffusive shock acceleration, acts like a natural particle accelerator of unimaginable scale. The proton surfs the shockwave, gaining energy with every pass until it eventually escapes, now a genuine cosmic ray flung into the galaxy. It is a beautiful and violent symmetry, the same explosion that forges heavy elements like iron and gold in its heart also acts as a natural slingshot, hurling the lightest atomic fragments across light years. This theory elegantly explains the origin of many cosmic rays, but it hits a fundamental limit. Even the most powerful supernova shockwave cannot account for the ultra-high energy bullets, the ones with the punch of a baseball. Their energy is simply too great, suggesting there must be even more monstrous engines lurking in the dark. On October 15, 1991, the quiet desert sky over Utah delivered a message that defied all understanding. A single, invisible projectile from the depths of space struck the upper atmosphere. It was not just another cosmic ray. The detector that witnessed the event, an array of mirrors whimsically named the fly's eye, recorded something that should not exist. The data revealed a particle carrying an energy of about 300 electron volts. To translate that from the abstract language of physics, this single subatomic speck, likely a proton or an atomic nucleus, arrived with the kinetic energy of a baseball traveling at 90 miles per hour. Scientists struggling to comprehend the measurement gave it a name that perfectly captured their stunned disbelief, the "oh my God" particle. Think about that for a moment. A major league pitcher channels the coordinated power of muscles, tendons, and years of training to hurl a 5-ounce ball of cork and leather. The universe, through some unknown mechanism, packed an equivalent punch into something over 10 million times smaller. The energy was so absurdly high that it presented a genuine puzzle. According to our best theories, a particle with that much energy should not be able to travel very far through the cosmos at all. It should collide with the faint glow of photons left over from the Big Bang, the cosmic microwave background, and lose its energy in a series of dramatic crashes long before it could ever reach Earth. The existence of the "oh my God" particle meant one of two terrifyingly exciting things. Either our understanding of physics at these extreme energies was incomplete, or this projectile had come from somewhere terrifyingly close to our galactic neighborhood, a place where an engine of almost inconceivable power had just fired a shot across our bow. What kind of cosmic catastrophe could possibly serve as that gun? The "oh my God" particle forces us to confront a humbling seventh fact. The most energetic cosmic rays carry energies millions of times greater than anything our greatest machines can produce. Consider the Large Hadron Collider, humanity's most ambitious scientific instrument. It is a 27-kilometer ring of supercooled magnets buried beneath the border of France and Switzerland. After decades of work and billions of dollars, it can accelerate a proton to an energy of about 13 tera-electron volts. It is a monumental achievement, allowing us to smash particles together and peer into the fundamental laws of reality. Yet the universe operates with a casual, terrifying power that renders our efforts almost quaint. The "oh my God" particle arrived with an energy of 300 electron volts. To grasp that multiplier, you need to understand the scale. 1 electron volt is 1 million tera-electron volts. That single particle from the cosmos carried the energy of over 23 million Large Hadron Collider protons, all combined into one. It is the difference between a firecracker and a volcanic eruption. This disparity highlights a profound truth. For all our ingenuity, we are confined to a small corner of the physics playground. The universe itself is conducting violent, high-energy experiments on a scale we can scarcely comprehend, using natural accelerators of staggering power. These cosmic rays are the evidence, the data packets fired from those distant laboratories. They are not just particles, they are messages from the extreme, telling us that the laws of physics can be pushed to frontiers we have never seen, under conditions we cannot hope to recreate. What other impossible experiments is the cosmos running right now, in the dark between the stars? That single, impossible particle did not strike the ground. It could not. The eighth astonishing fact about cosmic rays is that we never detect the original traveler itself. Instead, we witness its spectacular and violent death in the sky. When one of these high-energy bullets, whether a modest proton or an "oh my God" behemoth, finally reaches Earth, it meets its end not with a whisper, but with a celestial fireworks display invisible to our eyes. Its target is the first molecule of air at the very top of our atmosphere, over 15 miles up. Traveling at nearly the speed of light, the cosmic ray collides with the nucleus of that air molecule with the force of a miniature Big Bang. In that instant, the colossal kinetic energy of the primary particle is converted into raw matter, spraying out a burst of secondary particles like subatomic shrapnel. This is the birth of what physicists call an extensive air shower. The initial explosion creates unstable particles called pions, along with a spray of new protons and neutrons. These new particles, still carrying immense energy, almost immediately collide with other air molecules, creating their own explosive bursts. Each collision breeds more particles, which then collide again. What began as a single point of impact rapidly blossoms into a cascading avalanche, a widening cone of secondary debris that races downward toward the surface. At the heart of this shower are exotic particles like muons, heavy cousins of the electron that can penetrate hundreds of meters of rock. By the time this invisible rain reaches the ground, the original cosmic ray has been multiplied into billions of secondary particles, spread across an area the size of a city block. The most energetic events can create a particle front over a kilometer wide. Our detectors on the ground, from simple Geiger counters to vast arrays of water tanks, do not see the cosmic gunshot. They hear the echo, the expanding ring of debris from a single, catastrophic impact in the thin air far above. It is a ghostly footprint, the only way we can perceive these messengers from the void. The ghostly footprint of an air shower is how we listen to the cosmos today, but the very first person to hear that faint signal had to rise above the clouds to find it. The ninth fact in our journey is a story of human daring that changed science forever, the discovery that started it all. In the early 20th century, scientists were puzzled by a persistent background radiation in the air. They assumed, logically, that it must be coming from the ground, from radioactive elements in the Earth's crust. But a young Austrian physicist named Victor Hess was not convinced. To settle the question, he devised a breathtakingly simple and dangerous experiment. He would take his radiation detectors, delicate electroscopes of their time, and carry them high into the sky. Between 1911 and 1912, Hess made a series of daring balloon flights, some reaching altitudes of over 17,000 feet, a realm where the air was thin and freezing. It was a perilous endeavor in an open basket, but the results were unequivocal and shocking. As he ascended, the level of ionizing radiation did not decrease. It increased, and dramatically so. At his highest altitudes, the radiation was 3 times stronger than at the ground. This was the crucial proof. The source of this mysterious energy was not beneath his feet, but above his head. It was coming from space. Hess had discovered cosmic rays, though he called them Herrenstrahlung, or radiation from above. His courageous flights proved for the first time that our planet is under a constant, invisible bombardment from the cosmos, a rain of energy that had been falling silently for all of Earth's history. For this monumental discovery, which opened an entirely new window on the universe, Victor Hess was awarded the Nobel Prize in Physics in 1936. He did not just measure a phenomenon, he unveiled a fundamental truth about our place in the cosmos, proving we are connected to the violent heavens by an endless, silent drizzle of atomic fragments. Victor Hess's discovery opened more than a new field of physics. It gave us a new way to see the universe. The 10th fact reveals that cosmic rays are not just energetic particles, they are a form of direct cosmic archaeology. This is what scientists now call multi-messenger astronomy. For centuries, our only window on the cosmos was light, from the visible twinkle of stars to the invisible pulses of radio waves and X-rays. Light tells us about an object's temperature, its motion, its chemical composition from afar. But cosmic rays offer something fundamentally different. When we detect one, we are not analyzing a photon that was emitted by a distant event. We are catching a piece of the event itself. We are sampling the actual matter that was forged in a stellar core, shredded in a supernova shockwave, or hurled from the chaotic disk around a black hole. That particle, that proton or ion nucleus, is a physical artifact. Its very composition is a direct clue to its origin. By measuring the ratios of different elements in the cosmic ray rain, scientists can perform a kind of celestial forensics. An overabundance of certain rare isotopes like lithium, beryllium, and boron acts as a fingerprint. These fragile elements are not cooked in large quantities inside stars. They are the shattered fragments of heavier atoms like carbon and oxygen, broken apart in violent collisions during their long journey through space. The amount of this cosmic shrapnel tells a story of how long the particle has been traveling, how much material it has smashed through on its way to us. So every time a detector registers a cosmic ray, it is not just measuring energy, it is catching a piece of celestial shrapnel, a bullet whose elemental makeup holds the history of its violent birth and its turbulent journey across the galaxy. It is astronomy not by looking but by touching. That celestial shrapnel we collect tells a story of elemental abundance. The 11th fact is that cosmic rays provide a surprisingly familiar chemical inventory of our galaxy. When scientists painstakingly analyze the endless rain, they find its composition is not random or exotic. It is, in essence, a well-mixed sample of the cosmic ingredients found throughout the Milky Way. Roughly 90 out of every 100 cosmic rays are single protons, which are nothing more than the bare, positively charged nuclei of hydrogen atoms. Hydrogen is the simplest and most abundant element in the universe, the fundamental fuel of stars, so its dominance in the cosmic ray flux makes perfect sense. Following that, about 9% are helium nuclei, often called alpha particles. These are the next most common building blocks, forged in the immense furnaces of the Big Bang itself. The final 1% is where the true diversity lies, a rich sprinkle of everything else. This includes nuclei of carbon, oxygen, neon, and magnesium, all the way up to iron. Iron holds a special place in this hierarchy, as it represents a natural endpoint for energy production in massive stars. The relative proportions of these elements in the cosmic ray rain mirror, with some intriguing tweaks, the general elemental abundance we observe throughout interstellar space. This cosmic mix is a crucial clue. It tells us that the accelerators are not somehow selecting for strange or rare materials. They are taking the ordinary stuff of the galaxy, the hydrogen and helium that fills the voids between stars, and simply hurling it with unimaginable force. The universe is not manufacturing special bullets, it is grabbing whatever raw material is on hand and launching it in a particle cannon. This simple fact connects the silent rain directly to the life cycle of the galaxy itself, a cycle of stellar birth, death, and elemental recycling written in a code of atomic nuclei. But that familiar mix of cosmic ingredients hides a fascinating anomaly. The 12th fact reveals that within the endless drizzle, we find rare and fragile elements that act as cosmic mile markers. Among the heavy nuclei, scientists detect surprising amounts of lithium, beryllium, and boron. These are not the typical cosmic heavyweights. In the grand scheme of stellar nucleosynthesis, the process by which stars forge elements, these three are scarcely produced. Stars do not cook them in large quantities, so why are they showing up in the cosmic ray rain? The answer lies in the violence of the journey itself. The primary cosmic rays, the ones originally launched by supernova or black holes, are often sturdy nuclei like carbon, oxygen, and iron. As these heavier bullets race across the galaxy at near light speed, they do not travel through a perfect vacuum. They navigate the thin, scattered gas of the interstellar medium. Every so often, one of these carbon or oxygen nuclei will score a direct hit on a stray proton or helium nucleus floating in space. The collision is catastrophic. The high-energy cosmic ray nucleus shatters like fine crystal, breaking apart into lighter fragments. This process, called spallation, is a cosmic game of atomic billiards. The heavier nucleus is the cue ball, and the interstellar gas atom is the target. The impact sprays out debris, and among that debris are the fragile isotopes of lithium, beryllium, and boron. Their presence is not a sign of their origin, but a record of destruction. The more of these fragile elements we detect relative to their parent elements like carbon, the longer the average cosmic ray has been traveling, smashing through the galactic medium. They are the chipped paint and dents on a cosmic bullet, telling us not where it was made, but how rough its journey has been. This silent rain of particles has a ghostly, tangible effect right here in our world. The 13th astonishing fact about cosmic rays is that they can reach down and literally change the information stored in your devices. It happens through a phenomenon known as a single event upset. When a cosmic ray, or more often one of its secondary muons, penetrates the delicate circuitry of a computer chip, it can deposit a tiny but critical charge as it passes through. That microscopic burst of energy is enough to flip a single bit of digital memory, changing a stored 0 to a 1 or a 1 to a 0. In that instant, a perfect piece of data becomes corrupted. For you, this might manifest as a mysterious, one-time software glitch, a frozen program, or a corrupted file that seemed to happen for no reason at all. But the implications scale dramatically with the importance of the system. In aviation, a single-bit flip in an aircraft's flight computer could theoretically cause a sensor to give a false reading. For spacecraft traveling beyond the protective shield of Earth's atmosphere, cosmic rays are a constant, nagging threat to their onboard computers, requiring special radiation-hardened chips and redundant systems. In the world of finance or critical infrastructure, an upset in a server could corrupt a transaction or disrupt control systems. It is a humbling reminder of our connection to the cosmos. The same violent processes that light up supernova and power quasars from billions of light-years away can reach into the heart of our most advanced technology and leave a minuscule digital fingerprint. Your computer does not just calculate, it weathers a silent storm from space, one random bit at a time. The universe's influence may reach far deeper than our technology. A 14th and highly debated fact suggests cosmic rays could be silent architects of our very weather. This idea centers on a subtle chain reaction high in the atmosphere. When a cosmic ray or its secondary particle streaks through the air, it can strip electrons from the molecules it passes, creating charged ions. These ions, the theory proposes, can act as seeds around which water vapor can more easily condense, forming the microscopic droplets that grow into clouds. More cosmic rays could, in principle, lead to more cloud cover. Since clouds reflect sunlight back into space, a greater flux of these particles from the galaxy might theoretically cool the planet by increasing Earth's overall albedo. It is a grand and provocative hypothesis, directly linking the violent death throes of distant stars to the patterns of rain and sunshine over our heads. The research, however, is fiercely contested, isolating the tiny signal of cosmic ray influence from the vastly more powerful drivers of climate, like greenhouse gases and ocean cycles, has proven enormously difficult. Some studies show a tantalizing correlation between historical cosmic ray flux and periods of global cooling, while others find no significant link at all. This remains one of the most fascinating frontiers in atmospheric science, not as settled fact, but as a brilliant question. It asks us to consider whether the long tendrils of galactic events might gently brush against the delicate machinery of our climate, connecting the fate of our world to the rhythm of stellar explosions far beyond our solar system. That silent rain from the heavens has a history of delivering profound gifts to physics. The 15th monumental fact is that cosmic rays gave us our first glimpse of a mirror universe. The year was 1932, and a young physicist named Carl Anderson was studying cosmic ray tracks using a device called a cloud chamber. It was a simple yet brilliant instrument, a sealed container filled with vapor. When a charged particle from a cosmic ray shower zipped through, it would leave a trail of tiny condensation droplets like the jet contrail of a subatomic airplane. By examining these delicate tracks in a powerful magnetic field, Anderson could deduce a particle's mass and electric charge. One day, he observed a track that defied all expectation. It curved in the exact opposite direction that an electron should. Its curvature suggested it had the same mass as an electron, but it carried a positive charge instead of a negative one. It was as if he had found a photographic negative of reality. Anderson had discovered the positron, the antimatter counterpart of the electron. This was not a theoretical prediction confirmed in a controlled lab experiment. It was a piece of the cosmos reaching down and showing us something utterly new. That single, elegant track in a cloud chamber was the first direct experimental evidence that antimatter was real, a fundamental component of the universe predicted by Paul Dirac's equations just a few years earlier. Cosmic rays, in their chaotic violence, had acted as a natural particle collider, creating this exotic substance and delivering its signature right into our hands. It was a discovery that reshaped our understanding of matter itself, all thanks to a ghostly trail left by a visitor from deep space. The discovery of antimatter was just the beginning of the cosmic rays' gifts. That same chaotic rain from space soon delivered another particle that left physicists utterly baffled. In the years following Carl Anderson's work, researchers using cloud chambers kept seeing strange tracks. These particles curved under magnetic fields just like electrons, but their curvature was all wrong. They were not bending as sharply, meaning they were heavier, much heavier. Calculations showed they had about 200 times the mass of an electron, but they carried the same negative charge. It was as if nature had made a copy of the electron, but poured extra mass into it for no apparent reason. This new particle was named the muon. Its existence was a complete shock to the physics community. At the time, the theoretical framework for understanding matter was built around the electron, the proton, and the neutron. There was no prediction, no need, and no place for a heavy electron. It served no obvious purpose in the architecture of atoms or the forces that held them together. The bewilderment was perfectly captured by the Nobel laureate Isidore Rabi in a now legendary remark. Upon hearing of the muon's confirmation, he asked with a mix of humor and profound confusion, "Who ordered that?" The question resonated because it was so perfectly apt. It was as if the universe had sent down a component for a machine no one had designed, an answer to a question no one had thought to ask. The muon was not just a new particle, it was a message that our understanding of the subatomic world was still painfully incomplete. Cosmic rays had once again acted as a rogue delivery service, dropping off a puzzle that would take decades to unravel and ultimately point the way to an entire new family of fundamental particles. The muon was a cosmic clue delivered by accident, but today we hunt these particles with instruments of staggering scale. To catch the most elusive and energetic cosmic rays, scientists have built a detector so vast it can only be comprehended from the air. The Pierre Auger Observatory sprawls across the high plains of Argentina, a scientific instrument covering 3,000 square kilometers, an area larger than Luxembourg. From the ground, it looks like an endless, arid landscape dotted with strange, solitary tanks. But these are not water tanks for livestock. Each one is a pristine, 12,000-liter container of ultra-pure water, lined with sensitive light detectors. 1,600 of these identical tanks are arranged in a precise grid, each separated by 1.5 kilometers, creating a colossal net to catch the ghostly footprints of giant air showers. When an ultra-high-energy cosmic ray slams into the atmosphere above the observatory, it triggers a cascading avalanche of particles. The heart of this shower travels faster than the speed of light in air, a condition that creates a faint, fleeting pulse of ultraviolet light called nitrogen fluorescence. 24 specialized telescopes positioned on the observatory's perimeter stare at the night sky, their mirrors tuned to capture this ethereal blue glow, tracing the shower's development across the heavens. Simultaneously, the secondary particles, the muons and electrons from the cascade, finally reach the ground. When they streak through the dark water in one of the tanks, they travel faster than light can move in that medium, producing a shockwave of blue light called Cherenkov radiation. The detectors in each tank record this flash and its precise timing. By combining the fluorescence map from the telescopes with the timing data from the tank array, scientists can perform a breathtaking feat of triangulation. They can reconstruct the original cosmic ray's trajectory, its energy, and even its mass with incredible precision. It is astronomy performed not with lenses, but with a continent-sized catcher's mitt, waiting for the universe to throw its fastest pitches. That colossal catcher's mitt in Argentina listens for the echoes of cosmic bullets, but to find the guns themselves, we need a different kind of witness. The 18th fact reveals a deeper connection in this cosmic violence, one that involves the most ghostly particles in existence. When those high-energy protons or nuclei from cosmic rays collide with matter, whether in a supernova shockwave or a cloud of interstellar gas, the wreckage does not just spray out protons and muons. These catastrophic impacts also forge torrents of neutrinos. Neutrinos are the universe's ultimate phantoms, particles with almost no mass and no electric charge. They are so indifferent to normal matter that trillions pass through your body every second without a single interaction, coming straight from the core of our sun. But the neutrinos produced alongside the most powerful cosmic rays are different. They carry staggering energies, a direct signature of the violent event that created them. And unlike their charged cosmic ray cousins, neutrinos have a supreme advantage. They travel in perfectly straight lines. Magnetic fields do not bend them, and they pass through entire galaxies as if they were empty space. If we could catch one of these high-energy neutrinos and trace its path backward, it would point like a flawless cosmic arrow straight back to its source. The challenge is catching a particle that barely notices the universe exists. For that, scientists built the strangest telescope on Earth, buried under the ice at the South Pole. The Ice Cube Neutrino Observatory is not a collection of lenses and mirrors. It is a cubic kilometer of the purest, darkest Antarctic ice, transformed into a giant particle trap. Engineers melted 86 holes, each over 2.5 kilometers deep, into the eternal ice sheet. Into these holes they lowered strings of basketball-sized light sensors, 5,160 in total, frozen in place forever. This three-dimensional grid hangs in the ice like a colossal chandelier, waiting in absolute darkness. When a rare, high-energy neutrino from deep space finally does interact with an atom in that ancient ice, it produces a muon moving faster than light can travel in the frozen medium. This creates a faint cone of blue Cherenkov radiation, a silent flash in the deep. The embedded sensors capture this light, mapping its precise path and timing. By reconstructing this ghostly signal, IceCube can determine the neutrino's energy and, most importantly, the exact direction it came from. It is astronomy by waiting for a phantom to cast a shadow in a block of ice, a shadow that finally points the way home. IceCube's phantom arrows point us toward the most terrifyingly powerful engines in the cosmos. The 19th fact brings us to the prime suspects for creating the highest energy cosmic rays, the monsters at the heart of certain galaxies. These are not just supermassive black holes which lurk quietly in most galactic centers, but ones that are actively feeding in a frenzy of destruction. When vast amounts of gas, dust, and even entire stars spiral into the gravitational well of such a black hole, they don't just vanish quietly. The material forms a searing, churning disk of plasma, heated to millions of degrees as it's torn apart by unimaginable forces. This chaotic feast does something extraordinary. It channels a fraction of that incoming matter and energy into two narrow, opposing beams that blast outward from the black hole's poles. These are relativistic jets, streams of charged particles accelerated to nearly the speed of light. They are not gentle flows, they are focused cannon blasts of pure energy that can stretch for millions of light years, far beyond the boundaries of their host galaxy. Within these jets, conditions reach extremes we cannot replicate. Intense shock waves and turbulent magnetic fields race along the jet's length. A single proton caught in this maelstrom could be tossed back and forth across these shock fronts for eons, gaining a tiny boost with each pass. Over distances spanning entire galaxy clusters, this natural acceleration process could, in theory, pump a particle up to those impossible energies we see in the oh my god particle. It is a cosmic particle accelerator on a scale that dwarfs all human imagination, using the gravitational energy of a black hole as its power source and the structure of space itself as its guide. An active galactic nucleus does not just shine with light, it functions as a titanic railgun, firing atomic bullets across the intergalactic void. These galactic railguns are not the only contenders in the hunt for the ultimate particle accelerator. A 20th fact introduces an event of such staggering, concentrated violence that it makes even an active black hole seem almost leisurely. Gamma-ray bursts are the single most powerful explosions we know of in the universe since the moment of creation itself. For a few fleeting seconds, a gamma-ray burst can outshine every star in 100 billion galaxies combined, releasing more energy than our Sun will emit in its entire 10 billion-year lifetime. This is not a slow, rolling explosion like a supernova. It is a focused, apocalyptic flash of the highest energy light, a scream of pure radiation. The leading theories point to two catastrophic origins. The first is the collapse of a truly monstrous star, dozens of times the mass of our Sun, into a black hole. The second, and perhaps even more violent, is the final, spiraling dance of two dead stars called neutron stars. When these ultra-dense corpses, each a city-sized ball of pure nuclear matter, finally collide, they unleash a cataclysm of unbelievable proportions. It is in the chaotic, hyper-magnetized wreckage of such an event that physicists see a perfect, if terrifying, particle accelerator. The same relativistic jets that are thought to power the burst, blasting out at near light speed, would be threaded with unimaginably strong magnetic fields and riddled with shock waves. A proton or atomic nucleus caught in this maelstrom would not be gently surfacing a shock front for millennia. It would be violently wrenched and hurled, gaining astronomical energy in a heartbeat. The environment is so extreme, the forces so concentrated, that it could theoretically crank particles up to those elusive ultra-high energies, perhaps even beyond what we've seen. It is a particle gun that fires just once, with a blinding flash that announces the shot before vanishing forever into the dark. If a gamma-ray burst occurred anywhere in our galactic neighborhood, it would sterilize planets and rewrite the chemistry of solar systems. From a safe, cosmic distance, however, its fading echo might just carry the fingerprints of the most energetic particles in existence. There is a theoretical speed limit for the universe's fastest bullets. This is the 21st fact, known as the Greisen-Zatsepin-Kuzmin cutoff, or simply the GZK limit. It is not a law written in a book, but a barrier woven into the very fabric of space. The principle is elegant yet severe. Space is not an empty, cold void. It is filled with the faint afterglow of creation itself, the cosmic microwave background radiation. This is the cooled remnant of the Big Bang, a bath of low-energy photons that permeates every cubic centimeter of the cosmos. Now, imagine one of those ultra-high-energy protons, an oh-my-god particle, racing across intergalactic space. As it travels at over 99.999999999% of light speed, from its own perspective, the gentle cosmic background radiation is no longer a faint microwave glow. Due to the extreme effects of relativity, that radiation is blue-shifted into a barrage of high-energy gamma rays. For the proton, it is like running face first into a relentless hail of energetic particles. Eventually, the proton will collide with one of these gamma-ray photons. The crash is transformative. The impact creates new particles, typically a short-lived particle called a pion. In that moment of creation, the proton loses a significant chunk of its precious kinetic energy. Over a distance of about 150 million light-years, these repeated collisions should drain even the most powerful cosmic ray down to an energy below a certain threshold, the GZK cutoff. It acts as a cosmic horizon. We should not be able to see particles from beyond that distance because their energy would have been eroded away by the ancient light of the universe itself. Yet we do. The detection of particles like the oh my god particle with energies far above this predicted limit presents a profound contradiction. It means one of two thrilling possibilities. Either these cosmic rays did not travel very far at all, implying there is a monstrously powerful accelerator terrifyingly close to our own galactic neighborhood, or our understanding of physics at these extreme energies is incomplete. The universe, it seems, is either hiding a gun in our backyard, or it knows a way to break its own speed limit. The GZK limit defines a horizon for these particles, but within our own galaxy, their influence is immediate and profound. These high-energy particles are more than just messengers or stray bullets. They are active participants in the ecology of the Milky Way. They provide a crucial, invisible service by ionizing the dense, cold clouds of gas and dust where new stars are born. In the frigid darkness of these interstellar nurseries, atoms and simple molecules float in a near-perfect vacuum. For chemistry to happen, for bonds to break and form, those molecules often need a little push, a spark of energy to get reactions started. That spark comes from a cosmic ray. When one of these particles tears through a molecular cloud, it strips electrons from the atoms it passes, creating a trail of charged ions. These ions become the catalysts for a surprisingly rich chemistry. They can trigger chains of reactions that build up from simple hydrogen gas to more complex molecules like carbon monoxide, water, and even organic compounds such as methanol or formaldehyde. In the deepest, coldest parts of these clouds, where starlight cannot penetrate to provide energy, cosmic rays are the only source of ionization. They are the agitators in the dark, stirring the primordial soup and allowing the molecular building blocks of the universe to assemble. Without this constant, subtle drizzle of high-energy particles, the interstellar medium would be a far more inert and chemically simple place. The galaxy would lack the rich molecular inventory needed to form not just stars, but the planets and potentially the chemistry that leads to life itself. This invisible rain becomes a deadly downpour beyond the safety of our world. The 23rd fact is a stark, practical challenge for our future in space. Cosmic rays present one of the most formidable obstacles to human exploration, especially for a journey to Mars. Here on Earth, we live under a double shield. Our planet's thick atmosphere acts as a protective blanket, forcing incoming cosmic rays to shatter into harmless secondary particles high above our heads. More crucially, Earth's powerful magnetic field creates a vast, invisible force field called the magnetosphere. This field deflects the majority of charged particles from the Sun and a significant portion of galactic cosmic rays, bending them away from the surface and toward the poles where they create the auroras. An astronaut in deep space or on the surface of the Moon or Mars has lost both of these defenses. They are exposed to the full, unfiltered flux of galactic cosmic radiation. This is not like the radiation from a medical X-ray. It is a continuous, penetrating assault of high-energy atomic nuclei. These particles are so energetic that they can tear through the hull of a spacecraft and the suits of astronauts, smashing directly into human cells. The damage is insidious and cumulative. When one of these high-speed nuclei plows through living tissue, it doesn't just ionize atoms along its path. It can shatter DNA strands in a way that is difficult for the body's repair mechanisms to fix correctly. This significantly raises the lifetime risk of developing cancer. But perhaps more worryingly for a mission lasting years, studies suggest this radiation could also harm the central nervous system, potentially leading to cognitive impairment, memory issues, and slowed reaction times during the flight itself. Imagine the irony. The very particles that carry messages about stellar life and death could threaten the lives of those trying to reach new worlds. Shielding a spacecraft against such penetrating radiation is enormously difficult, requiring impractically thick walls of material like water or lead, which would make launching any vessel impossible with current technology. For now, mission planners are left with grim calculations, balancing acceptable risk against the dream of setting foot on another planet, with the silent reign of the cosmos as their constant, unwelcome companion. That silent, isotropic drizzle may finally be revealing its first faint fingerprints. The 24th fact is a story of meticulous cosmic cartography, the hunt for anisotropy. For over a century, cosmic rays have appeared to arrive from every direction with equal probability, a perfect, featureless fog that obscured their origins. But physicists have long suspected that at the very highest energies the fog must thin. The logic is compelling. Those ultra-high energy cosmic rays, the ones with the energy of a baseball, are so powerful that the galaxy's magnetic fields should struggle to bend their paths completely. Their trajectories, while still scrambled, might retain a faint memory of where they came from, pointing just slightly more often from one patch of sky than another. Finding these imbalances, these anisotropies, is like trying to hear a whisper in a hurricane. It requires catching enough of these incredibly rare particles to build a statistical map of the sky. The Pierre Auger Observatory, with its continent-sized net, has been patiently compiling this map for years, and recently the data has begun to show a signal. At energies above 8 exaelectron volts, the cosmic ray rain is no longer perfectly uniform. The observatory's data reveals a broad, diffuse excess, a hotspot, in a direction roughly opposite the center of our own Milky Way galaxy. This is a crucial clue. It suggests these mighty particles are not coming from within our galaxy, but from beyond it. The hotspot seems to point toward a region of space dense with nearby galaxies and galaxy clusters, a celestial metropolis where the monstrous engines of active black holes are more common. This anisotropy is not a sharp pinprick pointing to a single quasar. It is a smeared statistical glow, exactly what we would expect if the particle's paths were still tangled by intergalactic magnetic fields, but not completely erased. It is the first tentative evidence that we are finally, after all this time, beginning to trace the cosmic bullets not just to their final echo, but back toward the guns that fired them. That smeared hotspot in the Auger data points a finger beyond our own galactic walls. This leads us to the 25th and perhaps most humbling fact in our journey. The very highest energy cosmic rays are likely not native to our Milky Way. They are extragalactic immigrants having undertaken a voyage of staggering distance and time. The evidence for this is written in their energy and their distribution. Remember the GZK limit, that theoretical speed bump created by the cosmic microwave background. For a proton to arrive here with the energy of an oh my god particle, it could not have traveled more than about 150 million light-years without being slowed down by that relentless photon hail. This immediately rules out sources within our own galaxy for the most extreme events, as our entire Milky Way is only 100,000 light-years across. The particle simply did not have enough room inside our home galaxy to lose that much energy, meaning it must have started its journey outside in the intergalactic void. Furthermore, the anisotropy maps, those first hints of a pattern, show an excess coming from a general direction away from the galactic plane, pointing toward the vast cosmic structures of our local universe. These particles are intergalactic travelers. They began their life in a foreign galaxy, perhaps one with a ferociously active core or a cataclysmic stellar collision. They were then hurled into the profound emptiness between galaxies, a space so vast and lonely it defies human comprehension. For hundreds of millions of years, this single atomic nucleus has raced through that darkness, a solitary speck on a journey longer than the age of the dinosaurs on Earth. All the while, the weak magnetic fields that permeate the cosmic web have gently, persistently twisted its path, erasing the precise address of its origin. By the time it finally plunges into our atmosphere and creates a shower we can detect, its story is ancient and its home galaxy is lost. We are catching the final, dying echo of a scream that began in a galaxy far, far away, so long ago that the continents on our own planet were in completely different positions. What cataclysm in that distant island universe was powerful enough to launch a single proton on a journey across the cosmic ocean? The shape of this cosmic rain tells a hidden story of its own. If you were to plot the number of cosmic rays arriving at Earth against their energy, you would not see a simple, smooth curve. Instead, the graph reveals a dramatic, jagged landscape with two unmistakable landmarks scientists call the knee and the ankle. It is a cosmic fingerprint, and each bend holds a clue about where these particles come from and how they were made. At lower energies, the spectrum is steep, meaning there are vastly more low-energy particles than high-energy ones. Then, at around 10 to the power of 15 electron volts, the line takes a sharp turn downward. This is the knee. The flux of particles drops off much more steeply beyond this point. Physicists interpret this bend as a signature of change. It likely marks the upper energy limit for cosmic rays accelerated within our own Milky Way galaxy, particularly by supernova shockwaves. Those stellar explosions are powerful, but they are not infinitely powerful. They can only pump particles up to a certain maximum energy before the mechanisms break down or the particles escape the accelerator. The knee is that boundary, the point where the galaxy's most common particle guns begin to run out of steam, but the story does not end with that steep decline. As we follow the graph to even more ridiculous energies, around 10 to the power of 18 electron volts, something remarkable happens. The line suddenly flattens out. This is the ankle. The rate of decrease slows dramatically, meaning these ultra-high energy particles, while incredibly rare, are more common than they should be if the knee's trend continued. This flattening is a major clue. It strongly suggests that a new population of cosmic rays is beginning to dominate. These are not the galactic particles that hit their limit at the knee. The ankle signals the growing influence of the extragalactic immigrants, the particles born in far more violent engines outside our galaxy. Their acceleration mechanisms, perhaps tied to active black holes or colliding neutron stars, operate on a completely different scale, capable of reaching energies that make supernova look tame. So this simple graph, with its two bends, is a map of a cosmic changing of the guard. The knee shows where our galaxy's influence wanes, and the ankle reveals where the true monsters of the intergalactic void begin to make their presence known. That cosmic fingerprint in the energy spectrum tells a story of galactic and extragalactic origins, but the influence of these particles may strike much closer to home, in the very storms that rumble over our heads. The 27th fact presents a startling hypothesis. Cosmic rays might be the hidden spark that triggers lightning itself. Within the towering, turbulent heart of a thundercloud, a colossal electric potential builds up, separating positive and negative charges across vast volumes. For a lightning bolt to bridge that gap, the air, which is normally a good insulator, must first become a temporary pathway for electricity. Something needs to create an initial channel of ionized air, a conductive trail for the main discharge to follow. This is where the silent rain from space may play a decisive role. The theory suggests that a high-energy cosmic ray secondary particle, like a muon or an electron, can streak through a developing thundercloud. As it does, it can rip electrons from the air molecules in its path, creating a thin, straight line of charged particles. Think of it as drawing a faint, conductive pencil line across a blank sheet of insulating paper. This ionized trail, known as a runaway electron avalanche, drastically lowers the electrical resistance along its length. It provides the perfect, microscopic weakness for the pent-up electric field in the cloud to exploit. In that instant, the built-up energy focuses onto that trail, superheating the air into a searing plasma and unleashing the blinding, earth-shaking bolt we see as lightning. It is a staggering connection. The same particles born in stellar cataclysms light years away could be acting as natural spark plugs in our own atmosphere, connecting the fury of a dying star to the flash of a terrestrial storm. While the exact mechanisms are still an active area of research, the idea beautifully illustrates how the cosmos is woven into the most dramatic phenomena on our own planet, a reminder that the universe speaks not just in whispers but sometimes in thunderclaps. The invisible particles that seed lightning also write the history of our own species into the very fabric of ancient objects. Cosmic rays provide the clock by which we measure the human past, a process known as radiocarbon dating. It begins high in the atmosphere, where a constant stream of cosmic ray neutrons, secondary particles from that endless rain, collide with the most common gas of all, nitrogen. When a neutron strikes a nitrogen-14 nucleus, it triggers a tiny atomic transformation, kicking out a proton and converting the nitrogen into an unstable, radioactive isotope, carbon-14. This newly forged carbon atom quickly bonds with oxygen to form carbon dioxide, which then mixes evenly throughout the global atmosphere. Plants absorb this tagged carbon dioxide during photosynthesis. Animals eat the plants, and so the radioactive carbon-14 enters the food chain, becoming a tiny, ticking component of every living thing on Earth. For as long as an organism is alive, it constantly replenishes its supply of carbon-14, maintaining a steady, known ratio with the stable carbon-12 in its tissues. But the moment it dies, that intake stops, the clock starts. Carbon-14 is unstable with a half-life of 5,730 years. This means that after that span, half of the carbon-14 atoms in a sample will have decayed back into nitrogen. After another 5,730 years, half of the remaining half will be gone, leaving only a quarter of the original amount, and so on. By meticulously measuring the minuscule remaining fraction of carbon-14 in an ancient piece of wood, a fragment of cloth, or a charred seed, scientists can calculate how many half-lives have passed since that organism died. This turns a piece of charcoal from a prehistoric campfire into a calendar, a splinter from a Viking longship into a historical document. Every time an archaeologist holds a relic and determines its age, they are not just reading the Earth, they are reading a message written by the stars. The cosmic rays that streak in from dying suns and colliding galaxies become the silent scribes of human history, their atomic signatures allowing us to trace the rise of civilizations, the spread of agriculture, and the footsteps of our ancestors across millennia. Our planet's magnetic shield is not the only one that shelters us. The Sun itself creates a vast protective bubble known as the heliosphere, an invisible frontier where the solar wind, a stream of charged particles flowing from the Sun, pushes back against the incoming tide of galactic cosmic rays. For decades, our understanding of this cosmic equilibrium was based on measurements taken from within this protective cavity. But to truly know the rain, you must step out from under the roof. Humanity has done exactly that, not with a person, but with a pair of robotic ambassadors launched in the golden age of exploration. The Voyager 1 and Voyager 2 spacecraft, after their historic tours of the outer planets, kept going. They sailed on into the void, their cameras long since shut down, but their cosmic ray instruments still patiently listening. Their decades-long journey was a slow ascent out of the Sun's influence. Then, in 2012 and 2018 respectively, each probe crossed a mysterious boundary called the heliopause. This is the final frontier of the solar system, the place where the outward pressure of the solar wind finally gives way to the interstellar medium, the true ocean of the galaxy. The moment Voyager 1 crossed that threshold, its cosmic ray detectors registered a dramatic and permanent change. The count of lower energy particles from our Sun plummeted. Simultaneously, the flux of high-energy galactic cosmic rays, the true background rain of the Milky Way, surged by nearly 100%. For the first time in history, a human-made object was directly sampling the unaltered cosmic ray environment of interstellar space, free from the filtering effect of our star's magnetic personality. The data was a revelation, confirming models and revealing surprises, like unexpected variations in the cosmic ray density just outside the heliopause. These twin spacecraft, now over 15 billion miles from home and receding further every day, have become our most distant weather stations, reporting back on the true conditions of the galactic sea we all sail through. Their faint signals, taking over 21 hours to reach Earth, carry a simple, profound message. We have finally measured the rain as it falls in the open ocean beyond our sun's protective shore. The silent drizzle that writes our history may also have written the very code of life. This brings us to a 30th and profoundly provocative idea. Cosmic rays might have played a quiet background role in the grand story of evolution itself. We know this radiation can damage DNA, flipping bits in our computers and posing a risk to astronauts. But on Earth, over the vast expanse of geological time, this effect transforms from a hazard into a potential creative force. The constant, low-level bombardment by cosmic ray secondaries like muons has provided a steady, gentle source of genetic mutations for billions of years. Most of these random changes to an organism's DNA are neutral or harmful, but on rare occasions, a mutation can confer an advantage, a new trait that helps a creature survive and reproduce in a changing environment. This variation is the raw material upon which natural selection acts. Without mutation, evolution would eventually grind to a halt, lacking new traits to test against the world. Cosmic rays, along with other natural sources of radiation like radioactive elements in rocks, have contributed to this essential mutation rate. They have been a persistent, if minor, ingredient in life's recipe for change. Imagine the deep past, a primordial landscape under the same starry sky we know today. As early life forms basked in shallow seas, cosmic rays, along with ultraviolet light from the sun, were subtly altering their genetic blueprints. Most alterations led nowhere, but over millions of years, a fortunate few might have helped a microbe process a new chemical or allowed a plant to grow a slightly sturdier stem. It is not that cosmic rays directed evolution. They did not aim for complexity or intelligence. They simply provided a whisper of randomness, a cosmic roll of the dice that life on Earth could use. This idea reframes the silent rain from a mere physical phenomenon into a potential participant in the biological drama of our planet. The same particles that trace their origin to exploding stars may have contributed in an infinitesimally small way to the genetic diversity that eventually led to the wonder of a forest, the flight of a bird, and the curiosity of a mind looking up at the stars and wondering where it all began. The ghostly footprint of an air shower is not caught by a single instrument, but by an army of them working in silent unison. To reconstruct the story of a single cosmic bullet, scientists deploy vast grids of identical detectors spread across miles of remote landscape, lying in wait like a dormant, continent-sized nervous system. Each unit in this array is a simple sentinel, often just a sealed tank of pure water or a block of plastic scintillator paired with a sensitive light sensor. They sit alone under the open sky, spaced a kilometer or more apart, connected only by precise GPS timing. Their operation is a masterpiece of coordinated simplicity. When an ultra-high-energy cosmic ray strikes the atmosphere above, it triggers the cascading avalanche of an extensive air shower. Billions of secondary particles, the muons and electrons from that high-altitude explosion, race toward the ground in a widening, invisible disk. As this particle front sweeps across the array, it does not hit all the detectors at once. It passes over them in a wave like a silent thunderclap expanding across the land. Each detector that is touched records a flash of light, the telltale Cherenkov glow from a particle moving faster than light can travel in water or plastic. Crucially, each detector also stamps that flash with an exact time, accurate to within a billionth of a second. This is the key. By analyzing the precise sequence of flashes which detectors lit up and in what order, supercomputers can perform a breathtaking feat of triangulation. They trace the wave front backward, calculating its angle and its core, the point on the ground where the shower was most intense. From the density of particles at that core, they can deduce the colossal energy of the original cosmic ray. And from the shape and timing of the wave, they can estimate its direction, untangling the first faint hint of where in the sky the journey began. It is astronomy by listening to the patter of an invisible rain, using a net so wide it can catch the echo of a single drop falling from the edge of the universe. Our local star is a fickle guardian against the galactic storm. The sun does not just provide light and warmth, its magnetic personality actively shapes the invisible rain that reaches our planet. This is solar modulation, a cosmic tug-of-war playing out across the entire solar system. The sun constantly exhales a stream of charged particles, the solar wind, which carries the sun's own magnetic field out into space. This creates a vast teardrop-shaped bubble called the heliosphere, an invisible magnetic fortress that envelops all the planets. For the incoming hail of galactic cosmic rays, this bubble is not a solid wall but a chaotic magnetic maze. Lower energy cosmic rays, those with less punch, find themselves battered away by these tangled magnetic fields carried on the solar wind. They struggle to penetrate deep into the inner solar system where Earth resides. The strength of this magnetic shield is not constant. It ebbs and flows with the sun's 11-year activity cycle. During solar maximum, when the sun is covered in sunspots and prone to violent flares and coronal mass ejections, its magnetic field is especially turbulent and powerful. The solar wind blows harder, and the heliosphere becomes a more effective cosmic ray deflector. At these times, the flux of galactic cosmic rays measured here on Earth can drop by a significant margin, sometimes as much as 20%. Conversely, during the quiet period of solar minimum, the sun's magnetic shield weakens, the solar wind calms, and the magnetic maze within the heliosphere becomes easier to navigate. More cosmic rays slip through the defenses, and the background count we measure slowly rises. It is a rhythmic, decades-long breathing of our star, directly influencing the intensity of the atomic drizzle that penetrates our atmosphere. This modulation provides a living record, linking the sun's hidden magnetic moods to the silent rain from the galaxy, reminding us that even our local star holds sway over the particles from distant cataclysms. The sun's protective rhythm is a known variable, but some cosmic ray data points to something far more alien in our past, when the most energetic particles seem to defy every known law of acceleration. Science must turn to even more radical possibilities. This leads to a 33rd fact so speculative it borders on the edges of cosmology, the idea of top-down models. The conventional story, the bottom-up model, is one of building energy from nothing. A supernova shockwave or a black hole jet takes a low-energy proton and painstakingly pumps it up over immense distances, like a cosmic water wheel gradually lifting a bucket. But for the very highest energy events, some physicists wonder if this process is simply too slow, too inefficient. What if, instead of building up from the bottom, these particles are the shattered fragments of something that started at the very top? Imagine a mountain crumbling. You do not need to explain how each individual rock was laboriously carried up the slope. The rocks were simply there when the peak collapsed. Top-down models propose that ultra-high energy cosmic rays are the debris from the decay or annihilation of primordial monsters, hypothetical relics left over from the first instance of the Big Bang itself. These are not objects in any normal sense, but defects in the very structure of spacetime, frozen into the fabric of the universe as it cooled. Candidates include cosmic strings, hypothetical one-dimensional cracks in reality with the mass of a mountain range packed into every inch, or magnetic monopoles, solitary particles carrying a north magnetic charge without a south. If such entities exist and are unstable, their catastrophic breakdown would release a torrent of energy, spraying out ultra-high energy particles as decay products. In this view, an oh my god particle is not a bullet carefully accelerated by a cosmic gun. It is a piece of shrapnel from the explosion of a cosmic artifact, a fragment of a singularity that has been slowly unraveling since the dawn of time. It is a theory born of necessity, a glimpse into the kind of wild, beautiful ideas we must entertain when the universe sends us a message that our textbooks cannot yet decode. While some detectors listen for the echoes of single, mighty bullets, others are built to watch the entire battlefield at once. Perched at an altitude of over 13,000 feet on the slopes of the Sierra Negra volcano in Mexico, the High-Altitude Water Cherenkov Observatory, or HAWK, is a panoramic sentinel. Its design is elegantly simple, yet its purpose is vast. Instead of a sparse grid of detectors spread across a continent, HAWK packs its power into a dense array. 300 large, dark tanks, each holding 200,000 liters of ultra-pure water, are arranged shoulder to shoulder across the high mountain plain. Inside each tank, suspended in the darkness, are 4 sensitive light detectors. This is not a telescope that points, it is an eye that stares unblinkingly at the entire overhead sky, 24 hours a day, 7 days a week. Its constant vigil is for the faint, blue Cherenkov glow created not in the ice or in distant water tanks, but in the very air above it. When a cosmic ray, or more often, a gamma-ray photon slams into the atmosphere directly above the array, it creates a cascade of secondary particles. These particles rain down onto the tanks in a concentrated downpour. As they plunge into the dark water, they travel faster than light can move in that medium, and each one emits a faint, conical flash of that characteristic blue light. The key is the density of the array. Because the tanks are so close together, nearly all of them are hit simultaneously by the shower front. By comparing the precise timing and intensity of the flashes across all 300 tanks, HAWK computers can reconstruct the entire footprint of the shower with incredible detail, tracing its origin back to a specific point in the sky. This wide field view is its superpower. While other observatories might catch one ultra-rare, ultra-high energy event per week, HAWK sees the sky in a constant, sweeping scan. It monitors the entire overhead hemisphere every day, building up a living, dynamic map of the most energetic phenomena. It watches for the flicker of active galactic nuclei, the afterglows of gamma-ray bursts, and the steady glow of cosmic ray accelerators within our own galaxy. In the silent, thin air of that volcanic peak, HAWK does not wait for a single cosmic gunshot. It watches for the muzzle flashes lighting up the entire cosmic night. The silent rain that seeds lightning and writes history can also whisper a warning inside our most delicate machines. This 35th fact connects the cosmos to a frontier of human ingenuity, superconductivity. When certain materials are cooled to incredibly low temperatures, they enter a magical state where electricity flows with zero resistance, creating powerful magnetic fields and enabling technologies like magnetic levitation trains and MRI scanners. But this perfect state is fragile, a gossamer thin balance of quantum conditions. Enter the cosmic ray muon, a heavy, penetrating secondary particle from an air shower high above. As it streaks through a block of superconducting material, it does not just pass through silently. Along its path, it deposits a tiny but significant burst of energy, heating the material along a microscopic, needle-like track. In that instant, along that minuscule line, the local temperature can spike just enough to break the delicate superconducting state. The material reverts to normal conductivity for a fleeting moment before cooling back down. For most large-scale applications, this is a negligible blip, but for the next generation of technology, particularly ultra-sensitive quantum computers, it is a potential disaster. Quantum computers rely on maintaining coherent quantum states in superconducting circuits, states that are exponentially more fragile than classical superconductivity. A single muon-induced disruption could introduce an error, corrupting a calculation that might have taken days to set up. This means the engineers designing these machines cannot think only about shielding from earthly electromagnetic noise. They must also consider the architecture of their shielding to mitigate the random, penetrating drizzle from space. The universe, in its infinite complexity, has linked the death throes of distant stars to the error rate in a machine that may one day solve problems we cannot yet even conceive. It is a humbling design constraint written into the blueprint of the future by the ancient rain of the past. The sun itself is a source of cosmic bullets, but of a very different kind. This brings us to a crucial clarification, the 36th fact that separates two distinct storms. What we have been calling cosmic rays, the ultra-high energy messengers from across the galaxy, are more precisely termed galactic cosmic rays. They are the background drizzle, the ancient, steady rain from deep space, but our own star produces its own, more tempestuous squalls. These are solar energetic particles, or SEP. While both are showers of atomic fragments, their origins and characters could not be more different. Galactic cosmic rays are accelerated over millennia by distant titanic events. Solar energetic particles are born in the sudden, violent tantrums of our local star. During a powerful solar flare or a coronal mass ejection, when the sun blasts billions of tons of magnetized plasma into space, the chaotic magnetic fields within that eruption can act as a powerful, if localized, particle accelerator. It grabs protons and electrons from the sun's own atmosphere and whips them up to high speeds in a matter of minutes or hours. The result is a blast of radiation that can reach Earth in under an hour, riding the shockwave of the solar storm. These particles are dangerous, but for different reasons. While galactic cosmic rays are fewer in number but pack an incredible individual punch, solar energetic particles come in overwhelming numbers, a torrential downpour of lower energy radiation. This flood poses a more immediate and acute threat. For an astronaut on a spacewalk or a satellite in orbit, an SCP event is a code red emergency. The intense radiation can quickly overwhelm shielding, damaging electronics, frying camera sensors, and delivering a potentially lethal dose to human tissue. It is the difference between being slowly worn down by the relentless erosion of a distant ocean and being caught in a sudden, violent tsunami from your own backyard. Understanding this distinction is vital, for it tells us that the silent rain from the galaxy is not our only concern. The star that gives us life can, in an instant, turn its fury upon us. To escape the tangled echo of an air shower, science must rise above it. High-altitude balloons offer a breathtakingly simple solution, carrying delicate instruments to the very roof of our world. These are not the party balloons of childhood, but colossal envelopes of helium or hydrogen, some as large as football stadiums when fully inflated, capable of lifting payloads the weight of a car to the edge of space. At altitudes of 120,000 feet or more, they float in the serene stillness of the stratosphere, where 99% of Earth's protective atmosphere lies below. Here, the cosmic rain is still a direct drizzle, not yet shattered into the complex secondary storm we measure on the ground. Missions like NAS, a Super Tiger, and its predecessor, the Cosmic Ray Energetics and Mass Instrument, or CREAM, exploit this pristine vantage point. Their detectors, often intricate arrays of scintillators and silicon sensors, hang silently beneath the balloon, exposed to the near vacuum. They do not wait for a cascade. They catch the primary cosmic rays themselves one by one as they arrive from the galaxy. This allows for exquisitely clean measurements of the particle's true identity. their charge and their mass are free from the interpretive guesswork required when analyzing the debris of an atmospheric collision. For weeks or even months, these robotic sentinels drift on the polar winds, patiently compiling a census of the cosmic ray population directly, telling us not just about the echoes of violence, but about the actual bullets before they strike our planetary shield. It is astronomy performed not with telescopes, but with floating traps, capturing the messengers in their purest form as they finally reach the doorstep of our world. The pristine census taken by high-altitude balloons reveals a strange overabundance in the cosmic rain. Among the heavier particles, we find far more lithium, beryllium, and boron than the universe should logically provide. These are not the cosmic heavyweights forged in stellar furnaces. Stars produce them only in trace amounts, and they are fragile, easily destroyed. So why are they so common in the endless drizzle from space? The answer is written in the violence of the journey itself, a process called spallation. Think of a primary cosmic ray, a sturdy nucleus of carbon or oxygen fired from a supernova. As it races across the galaxy at near light speed, it is not traveling through a perfect vacuum. It navigates a thin haze of interstellar gas, mostly lone protons and helium nuclei. Every so often, over millions of years, this cosmic bullet scores a direct hit. The collision is catastrophic. The high-energy carbon nucleus does not just bounce off, it shatters like fine crystals struck by a hammer. This atomic fragmentation sprays out lighter debris, and among that debris are the very isotopes of lithium, beryllium, and boron we detect. They are not the original cargo, they are the chipped paint and dents, the cosmic shrapnel created from the destruction of something larger. Their relative abundance is a direct clock and an odometer. By measuring how much of this fragile material exists compared to their parent elements like carbon and oxygen, scientists can estimate how much material the average cosmic ray has smashed through. A higher ratio means a longer, more violent journey through the galactic medium. This overabundance is a key piece of forensic evidence. It tells us these particles are not fresh from the factory, they are weathered travelers. They have endured a long and punishing voyage across the galaxy, their very composition altered by countless near misses and direct hits, bearing the scars of their epic journey written in the language of atomic nuclei. The silent rain from the cosmos might carry whispers from the universe's greatest secret. The 39th fact is a breathtaking possibility. Cosmic rays could be our first direct signal from dark matter. This invisible substance outweighs all the stars and galaxies we see by a factor of 5 to 1. Its gravitational pull sculpting the cosmos, yet it has never been directly detected. We know it is there by the way galaxies spin and how light bends, but its fundamental nature remains physics' most profound enigma. Some of the leading theories, however, suggest a thrilling connection to the particles raining down upon us. Certain hypothetical dark matter particles, like weakly interacting massive particles, or WIMP, are not entirely stable. If they occasionally collide or decay in the dark halos surrounding galaxies, that annihilation could produce a spray of familiar standard matter particles. This would include protons, electrons, and crucially, their antimatter counterparts, positrons and antiprotons. This is where cosmic ray detectors become dark matter telescopes. For years, experiments like the Alpha Magnetic Spectrometer on the International Space Station and the Payload for Antimatter Matter Exploration and Light Nuclei Astrophysics, or PAMELA, satellite have been meticulously counting the antimatter in the cosmic ray flux. And they have found something intriguing, an unexpected excess of high-energy positrons. The number of these antimatter electrons is higher than it should be if they were only produced by conventional astrophysical sources like pulsars or supernova remnants. While pulsars remain a strong candidate to explain this anomaly, the tantalizing shadow of dark matter lingers. If the excess positrons or a similar anomaly in antiprotons cannot be fully explained by known cosmic accelerators, it could mean we are already collecting the fallout from dark matter annihilations happening right now in our own galactic neighborhood. Every time a detector registers one of these anomalous antimatter particles, it might not just be catching a piece of a star, it could be catching a fragment of the invisible universe itself, a tiny, shattered piece of the cosmic scaffolding finally revealing its presence. The atmosphere itself becomes the world's largest scientific instrument. For the most colossal cosmic ray events, the detectors on the ground are merely the final witnesses. The true observation begins over 15 miles up in the thin, cold air of the stratosphere, when an ultra-high energy particle, a true oh my god behemoth, slams into a molecule of nitrogen or oxygen. It does not just create a shower of particles. It also unleashes a silent flash of light invisible to human eyes. The cascade of secondary electrons moving at nearly the speed of light excites the nitrogen molecules in the air around them. As these molecules calm down, they release that pent-up energy not as heat or sound, but as a faint, ethereal pulse of ultraviolet light. This is nitrogen fluorescence, a ghostly blue glow that traces the path of the developing air shower as it races downward. To capture this fleeting signature, observatories like the Pierre Auger Array employ a ring of specialized telescopes that stare at the clear night sky, their mirrors tuned not to the stars but to this specific ultraviolet frequency. They see the sky not as a static canvas but as a dark sheet where, once or twice a month, a faint, fast streak of light silently paints the passage of a cosmic bullet. It is a breathtaking method, turning 100 cubic kilometers of empty air into a colossal light-sensitive chamber. The atmosphere is no longer just a shield or a filter. It is an active component of the detector, a medium that transcribes the violence of a particle's death into a code of faint photons, allowing us to watch the entire life story of a shower from its first explosive moment to its final, fading echo on the ground. Long before we built our mightiest machines, we had a natural laboratory falling from the sky. The 41st foundational fact is this: cosmic rays are the unsung midwives of modern physics. For the first half of the 20th century, they were our only window into the subatomic frontier, the sole source of particles energetic enough to smash apart and reveal their secrets. Every major collider today, from the Large Hadron Collider to its predecessors, stands on the shoulders of discoveries made in the silent rain. It began with Victor Hess's courageous balloon flights proving the radiation came from above. But the real revolution started when physicists like Carl Anderson and Patrick Blackett pointed simple cloud chambers at the sky. These devices, little more than sealed boxes of vapor, became portals. When a cosmic ray secondary particle zipped through, it left a ghostly trail of condensation, a signature in fog. By placing these chambers in magnetic fields, scientists could watch the trails curve, deducing a particle's charge and mass. It was like having a microscope for the universe, one that used the atmosphere itself as a sample, and what the universe showed them was a chaos of creation. From those delicate trails in vapor, an entire zoo of new particles emerged, each one a fundamental piece of reality we had never seen. The positron was the first, the mirror twin of the electron, proving antimatter was real. Then came the muon, that heavy, puzzling copy of the electron that left physicists asking who ordered it, but the rain kept delivering. Soon, tracks revealed the pion, a particle that mediates the strong nuclear force gluing atomic nuclei together. Then the kaon, a strange particle that hinted at a new quantum property called strangeness, a whole new layer to the rules of matter. Each discovery was a fragment of a larger puzzle, a clue to the forces that shape our reality. These were not abstract predictions confirmed in a controlled lab. They were gifts from the cosmos, pieces of a hidden blueprint delivered at random. Particle physics, as a field, was not born in a pristine laboratory with a chalkboard full of equations. It was born in the messy, unpredictable data of cosmic ray showers, in the patient analysis of thousands of photographs showing trails that bent the wrong way or split in strange directions. Every time we smash particles in Geneva today to hunt for the Higgs boson or dark matter, we are continuing an experiment that began with a cloud chamber on a mountaintop, waiting for a message from a dying star. Our search for the universe's particle accelerators is about to gain 100 new eyes. While we patiently map the cosmic ray rain itself, the next leap in understanding will come from watching the light these bullets produce. When an ultra-high energy cosmic ray collides with interstellar gas near its source, that violent impact does not just make more cosmic rays. It also produces the highest energy photons in existence, gamma rays. These gamma rays travel to us in perfect straight lines, carrying the unambiguous address of their birthplace. To catch them, a global collaboration is building the most ambitious gamma ray observatory ever conceived, the Cherenkov Telescope Array. Scattered across two pristine sites in the Chilean Andes and the Canary Islands, the CT will not be a single instrument, but a forest of over 100 individual telescopes of 3 different sizes. They will work in concert, staring at the same patch of night sky. Their target is not the gamma ray itself, which is absorbed by our atmosphere, but the faint blue flash of Cherenkov light from the particle shower the gamma ray creates. This vast array will see the gamma ray sky with a sensitivity 10 times better than any current facility, and with a resolution sharp enough to make out fine details in the most violent objects. While its primary mission is to catalog gamma ray sources, this is where the story circles back to our silent reign. By pinpointing exactly where and how gamma rays are produced, the CT will effectively map the cosmic ray factories themselves. It will show us the specific shockwaves in supernova remnants where particles are being whipped to high speeds. It will peer into the relativistic jets of active galaxies and measure the furious conditions there. Each gamma ray it detects is a witness to a cosmic ray being born. This new observatory will not catch the bullets, but it will photograph the muzzle flashes with such clarity that we will finally understand the mechanisms of the guns. It turns the universe's most violent neighborhoods into open books, written in the language of fleeting blue light. The silent drizzle from deep space has become a vital tool for protecting our technology in orbit. This 43rd fact reveals a practical application: cosmic ray weather forecasting. While we cannot see or feel this rain, a global network of ground-based monitors acts as a planetary rain gauge, measuring its intensity in real time. These are neutron monitors, simple yet robust instruments scattered from the polar ice caps to high mountain peaks. They do not catch the primary cosmic rays, but the secondary neutrons those rays create when they strike the upper atmosphere. The count rate on these monitors is a direct barometer for the state of the heliosphere, the vast magnetic bubble blown by our sun. When the sun is active with strong solar winds and turbulent magnetic fields, it pushes back against the galactic cosmic rays and the neutron count drops. During solar quiet, the count rises, but the crucial data comes from sudden, sharp dips called Furbush decreases. These occur when a coronal mass ejection, a massive cloud of magnetized plasma from the sun, blasts through the solar system. This cloud acts like a magnetic broom, sweeping galactic cosmic rays out of its path, causing the neutron monitor readings to plummet. For space weather forecasters, this is a critical signal. That sudden drop tells them a significant solar storm has erupted and is now traveling toward Earth. By analyzing the depth and shape of the Furbush decrease, they can estimate the strength and speed of the incoming storm. This information is no mere academic curiosity. It translates directly into actionable warnings. Airlines can reroute high-altitude flights away from polar routes, where radiation exposure is highest, protecting crew and passengers. Satellite operators can place sensitive instruments into safe mode, shielding them from the surge of solar energetic particles that often follows the initial magnetic cloud. In a world increasingly dependent on fragile technology floating in the void, forecasting the weather from our own star is essential, and it all begins by listening to the subtle changes in the ancient galactic rain. The universe's most powerful particle accelerators are perfect at hiding in plain sight. This 44th fact confronts a deeply frustrating paradox, the mystery of the empty sky. For the ultra-high energy cosmic rays, the ones with the punch of a baseball, we have strong theoretical suspects. They should be coming from the most monstrous engines in our cosmic neighborhood, the active cores of nearby galaxies or the remnants of recent cataclysms. We point our most sensitive telescopes in the direction suggested by the faint anisotropies, the statistical hot spots in the cosmic ray map, and sometimes we see nothing. No brilliant quasar, no swirling disk of a feeding black hole, no fading afterglow of a gamma-ray burst, just a quiet, dark patch of sky as empty as any other. It is as if a detective, after years of work, finally gets an address for a suspect, only to arrive and find a vacant lot. This emptiness is not a failure of observation, it is a profound clue. It means our understanding of these cosmic guns is still incomplete. Perhaps the accelerator is not a permanent, blazing beacon. Maybe it is a transient monster, a black hole that feasts in violent, brief bursts and then falls silent for centuries, its jet shutting off and leaving no visible trace by the time its particles reach us. Or perhaps the source is so shrouded in dust and gas that its light is completely absorbed, while the neutral particles and cosmic rays slip through unseen. Another possibility is even more intriguing. The particles themselves might be coming from a type of object we have not yet classified, a dark accelerator that operates in a wavelength or energy band we simply cannot see with our current telescopes. The empty sky is not an absence of evidence, it is evidence of absence, a silent challenge from the cosmos. It tells us that the most violent events in the universe may not always announce themselves with a flash of light, but only with the silent, atomic shrapnel they fire blindly into the dark. That empty sky is a mystery of the present, but the particles themselves are whispers from a past far more ancient than our own. The cosmic rays raining down upon us are not just messengers from distant space, they are travelers from deep time. Consider the journey of a single proton, accelerated by a supernova shockwave on the far side of the Milky Way. Once it escapes that violent cradle, it does not fly straight to Earth. It enters a labyrinth, the galaxy's tangled web of magnetic fields. Its path becomes a chaotic, meandering walk, a drunken stumble across 100,000 light-years. It bounces from one magnetic field line to another, zigzagging wildly, trapped in a cosmic pinball machine. This process stretches what should be a direct trip of perhaps 50,000 years into an epic voyage lasting 10 million years or more. The particle we detect today, that triggers a flash in a water tank on a mountainside, began its journey when our earliest human ancestors were just beginning to walk upright on the African savanna. It was traveling when mammoths still roamed the Earth. It has been wandering the dark corridors of the galaxy since long before the first pyramids were built, before the first cities, before the very concept of history. This immense age makes cosmic rays a unique kind of fossil, but not a fossil of bone or stone. They are a fossil of the galactic environment itself. By studying their composition, particularly the fragile isotopes of lithium, beryllium, and boron created through collisions during their long trek, we can read the conditions of the interstellar medium millions of years ago. We are not sampling the galaxy as it is now, we are sampling a preserved record of what it was like in a different epoch. The silent rain is an archive, and each drop is a data point from a chapter in our galaxy's history written long before our sun even ignited. There is a mathematical elegance hidden within the chaos of the cosmic rain. The 46th fact reveals a stunning pattern in the power of these particles, a pattern so consistent it points to a universal law. If you plot the number of cosmic rays arriving at Earth against their energy, you do not get a random scatter of points. you get a line of breathtaking smoothness, a perfect curve that holds true across an almost unimaginable range. This is known as a power law distribution. In simple terms, it means that for every time you increase the energy by a factor of 10, the number of particles you see drops by a predictable proportional amount. High-energy cosmic rays are incredibly rare, while lower-energy ones are vastly more common, and the relationship between their rarity and their power is exquisitely precise. This pattern spans over 11 orders of magnitude, from particles with the energy of a thrown stone to those with the punch of a professional fastball. That smoothness is the key. It tells us that the process which creates these particles is not a collection of separate, unique events. It is not that supernovae make one kind and black holes make another, stitching together a jagged graph. Instead, that perfect power law curve suggests a single, universal, and scale-free mechanism is at work across the cosmos. From the shockwave of a local supernova to the relativistic jet of a distant quasar, the same fundamental physics is operating, just on different scales and with different available energy. The leading candidate is a process called Fermi acceleration, where particles gain energy by repeatedly bouncing across turbulent magnetic shock fronts, like a pinball gaining speed with each bumper hit. The smooth power law is the signature of that process, a mathematical fingerprint proving that whether the accelerator is in our galactic backyard or a billion light-years away, the universe builds its most energetic bullets using the same elegant, relentless recipe. That universal recipe for cosmic bullets is not just for professional scientists to decode. The 47th fact is a beautiful democratization of discovery. You can join the hunt yourself. Around the world, a growing movement of citizen science projects is turning classrooms and backyards into outposts of cosmic ray research. Initiatives like the Cosmic Ray Observatory Project, known as CROP, and networks run by universities provide simple detector kits to schools and enthusiastic individuals. These are not multi-million-dollar water tanks, but often small, rugged plastic scintillators or even homemade setups using inexpensive components. When connected to a computer, they become a silent sentinel, counting the muons that rain down from cosmic ray showers. The magic happens when these individual detectors connect online, forming a distributed global array. A student in Tokyo, a teacher in Nebraska, and an amateur astronomer in South Africa all run their detectors simultaneously. When a particularly large cosmic ray air shower sweeps across the planet, its particle front might trigger dozens or even hundreds of these simple stations within a fraction of a second. By sharing their precise timing data over the internet, this grassroots network can triangulate the direction and size of the shower, just like the giant professional observatories do, but on a planetary scale. This is not a simulation or a classroom exercise. It is real data contributing to the global understanding of cosmic ray flux and distribution. It means a high school student can wake up and check if their detector helped pinpoint a cascade from a distant supernova remnant the night before. By participating, you are not just learning about cosmic rays, you are catching them, adding your own day to point to a map of the sky that is being drawn by thousands of curious people around the world. The silent rain from the galaxy becomes a shared experience, a cosmic conversation where anyone with a little curiosity and a simple device can listen in. The hunt for the universe's most extreme bullets includes a search for the heaviest shrapnel imaginable. We have talked about protons and helium, carbon and iron, but the cosmic ray rain may contain fragments far more exotic. At the very end of the periodic table, elements like gold, lead, and even uranium are forged in the most violent stellar deaths, like the collisions of neutron stars or rare types of supernova. If a dying star can create these heavy atoms, could its explosive fury also launch them into space as cosmic rays? This is the frontier of ultra-heavy nuclei detection, and it requires instruments of exquisite sensitivity. Satellites like NASA's Advanced Composition Explorer with its cosmic ray isotope spectrometer have orbited Earth for decades, patiently sifting through the rain, identifying individual nuclei by their atomic mass. They have found traces of elements all the way up to the brink of the periodic table. But the true prize, finding a cosmic ray nucleus of uranium or another actinide, remains elusive. Such a discovery would be a smoking gun. It would point directly to a specific type of cosmic catastrophe, because only the most neutron-rich environments, like those in merging neutron stars, can produce such heavy, unstable elements in abundance. To finally catch these rarest of bullets, a new generation of missions is being prepared. Instruments like the High-Energy Light Isotope E experiment, or HELIX, are designed to fly on high-altitude balloons above the obscuring atmosphere, with resolution sharp enough to weigh a single atom of gold or uranium hurtling at near light speed. Finding one would be like discovering a fleck of paint from a specific make and model of car at a crash site. It would tell us not just that a crash happened, but exactly what kind of vehicle was involved. The search for these ultimate fragments is a direct probe into the heart of the universe's most extreme alchemy, waiting for a single, impossibly heavy atom to tell us its story. This universal recipe for cosmic bullets is not a local craft. The rain we measure is not a peculiar feature of our own Milky Way. It is a fundamental weather pattern for any galaxy that lives and breathes. Across the vast cosmic ocean, every island of stars with ongoing stellar birth and death is generating its own invisible storm. Wherever massive stars lie fast and die young in supernova explosions, wherever black holes feed and fire jets into the void, the same physical processes take the raw material of that galaxy and launch it into a perpetual high-energy drizzle. Our galactic neighbors, like Andromeda, are undoubtedly shrouded in their own vast halos of these energetic particles, a silent, crackling aura invisible to our telescopes. This makes cosmic rays a universal signature of a dynamic and violent cosmos. They are not an anomaly, they are an inevitable byproduct of the very forces that drive cosmic evolution. The cycle is elemental. Stars forge heavy elements in their cores and in their explosive deaths, and those same deaths act as natural accelerators, hurling atomic fragments back into the interstellar medium. Those fragments then seed new generations of stars and planets, and the cycle begins anew. Cosmic rays are the energetic connective tissue in this grand loop, a constant reminder that creation and destruction are two sides of the same coin. The silent rain falling on Earth is just our local sample of a phenomenon that permeates the entire observable universe, a testament written in atomic nuclei that wherever there is change, where there is energy, there will be this invisible, energetic hail. The final and perhaps most important fact is that the greatest discoveries still lie ahead of us. We have journeyed through 50 astonishing truths about this silent rain, from its misnamed identity to its ancient age, from the baseball pitch of a single proton to its ghostly fingerprint in our digital world. Yet for all we have learned, the core mysteries remain brilliantly, tantalizingly open. We still do not know with absolute certainty the exact cosmic addresses of the guns firing the ultra-high energy particles. The statistical hotspots point to the intergalactic void, but the empty sky where we expect to see a brilliant source mocks our assumptions. Is the true accelerator a fleeting monster, a black hole that feasts and then falls silent, leaving only its bullets as a calling card? The question of how nature pumps a subatomic speck up to such impossible energies also defies a complete answer. We have the elegant blueprint of shock acceleration, but the details of how it operates in the relativistic jets of active galaxies or the wreckage of colliding neutron stars are still being sketched. Every new detection from observatories like Auger or IceCube adds a piece to this puzzle, but the full picture of the universe's ultimate particle accelerators remains just out of focus. And what of the bullets themselves? Their composition is a direct sample of the cosmos, but we have only begun to read its full language. What would the detection of a single uranium nucleus tell us about the specific alchemy of a neutron star merger? Could an anomalous spike of antimatter in the rain finally be the whisper of dark matter we have been waiting for? These are not small questions. They are the fundamental puzzles that drive entire fields of science forward. The hunt is very much alive, powered by larger detectors, sharper telescopes, and the enduring human curiosity that first led Victor Hess to ascend into the sky in a balloon over a century ago. The silent rain continues to fall, each particle a message in a bottle from a distant shore. We have learned to catch the bottles, and we are slowly, painstakingly learning to read them. The story they tell is far from over. This invisible conversation between the cosmos and our world has been ongoing since the birth of our planet. We have traced a journey from the silent, atomic shrapnel piercing our bodies every second to the unimaginable stellar cataclysms that fire these bullets across the void. Cosmic rays are far more than a scientific curiosity. They are a direct physical link to the universe's most violent events, a natural laboratory that has unveiled antimatter and new particles, and a forensic tool that allows us to date ancient artifacts and probe the chemistry of our galaxy. They challenge engineers protecting astronauts and quantum computers, and they may even whisper the first clues to the nature of dark matter. This silent rain connects the microscopic to the cosmic, the ancient past to the present moment, and the quiet of a laboratory to the fury of a quasar's jet. The next time you look up at a clear night sky, remember this: beyond the tranquil points of light, a storm is raging. An endless, high-energy drizzle is falling, connecting you directly to supernova, to black holes, and to the very edge of our understanding. That connection is the real story, written in particles too small to see, carrying messages from the most powerful engines in existence. We hope you'll join us for more deep dives into the profound mysteries waiting just beyond.